Hello and welcome to this final review of COSC 2425 Computer Organization and Architecture. And I will be going through the 4 chapters that you would be quizzed for during the final. So this is in my opinion the most important slide, where it shows the gradient policy that has been implemented since the beginning of the class. You are always given partial credit, even if the answer is incorrect. And so we are more interested in the process and your thought process, and what are the assumptions that you make, what are the answers that you can come up with given a specific problem. And so even if the answer is incorrect, you'd be awarded partial grading, partial score. For if however you choose to answer, and even if your answer is correct and you don't show any work, there will be a 75% penalty to that. So please try to write more details to your answers. And so anything goes, sentences, numericals or operations are also valid. So let's start with the MIPS datapad. And so the datapad has 6 components. Let's start with the instruction memory. So for the instruction memory, it contains the opcode, the register addresses, or the immediate. And so this is where basically your code is. So every instructions that any instruction that you are going to use is going to reference the instruction memory. And so keep in mind that what we mean here by registers are actually addresses for the register. And so, for example, you would have something like 001. This is the first register, and it means either like T0 or something. And so keep in mind that this is an address. For the registers here, however, it is a mapping of the value. So let me write it here. So it is going to be something like this. And here you have your first register, and here you have your last. And this address, you would address every register using it. So since we have 5 bits in every in the address space for every instructions, then we have a 32 registers that can be referenced. For the sign extension, it has 2 main functions. The first is extension. That means it is extending the immediate, the input, that is an immediate of size 16 bits, to 32 bits. And the sign means that it is preserving the sign of that particular immediate after the extension. So 2 functions: extend and preserve the sign. The ALU is used for any arithmetic or logical operation. So any R-type instructions or any branch or load and store would reference the ALU in order to either compute the offset, compute the operation, or evaluate the condition of the branching. The data memory is a space that is given, since the registers are very limited in space, and so the data memory serves as a space in order to expand and store more information or load more information, and therefore enables more application for the computing. Finally, there are the control signals, and these are, you would see them in the next slide, where we see a diagram. And these control signals are to enable or disable a component, and they change depending on which instruction you are using and which stage of the pipeline you are in, if the stage of the pipeline is if the pipelining is applicable. But mostly it depends on the particular instruction. So this is an example of the single cycle data path for MIPS, and we can draw the analogy from what I just said. This is your instruction memory. So what it does, it's you are reading your instructions, which are in a 32-bit size. Then you take every 5 registers to get your first register and the second register, if it is applicable. If it is not applicable, if you are not taking an immediate, then what you do is you load the immediate over here, and so you extend it to be used either in the ALU, and what you load here, here you get the address, and these two outputs will return the value. And so either you are using the immediate, in this case the immediate would be plugged in in the ALU, or it is going to be ignored and the second register would be plugged in. The first register would go and you do your computation. So if you have any results, it goes here, or if you are using memory write or read, then you would be given an address, and that address would return data that you are writing back. And so but if you are not using these and the memory is not working, then this is going directly to the write back, and you are going to write it in your register. In case you have a branch, then you get your branch in, and all you do is you shift and you calculate the new address for the program counter. When you do that, you write it and you set it in your program counter, and that is what constitutes a jump. So, like I said, every types of instructions uses different components, and this is a summary of the components that are used. For example, the R type, since an R type instruction is, for example, like an add T2, T1, and T0. So there is no memory, there is no sign extension because there is no immediate, and there is no control flow because there is no jumping. For the load, however, and read, you are using memory with the two signals. Either you are writing from memory or reading from memory. And so you are using the ALU because there is an offset. And you are using the sign extension because you are given the address which is and immediate, and so the load and store instructions use all of these three components. Finally, there's the branching instructions. There's the conditional branch and the unconditional branch. So for the conditional branch, they use the ALU in order to compare and to evaluate the condition. A sign extension because you are given an immediate. As for the unconditional branch, it doesn't use anything except the control flow, where you only apply a shift. You only apply a 2-bit shift, and then you perform the addition in the control flow, and so that would update your program counter. So this is an example of a load instruction. So here what we have is an address, right? So we have an address here, and here we have a shift. So what we do is we take this address and we add 4 for the offset. And whatever we get as value, not an address, as a value, would be put in, will be loaded rather in T0. So in the instruction memory, we fetch the instruction. We get the instruction. We fetch that particular line of code, and what we get is the following. We get an opcode, which is like 6 bits. We get the source register, or the base register in this case, which contain an address, like I just said. We get the offset of that address and the destination register. During the decode, so what happens? The control signals are generated based on the opcode. So for the opcode, we have memory read, since it is a load, ALU SRC, since we are calculating the offset, and mem to register, because we need to write back the data that we loaded from memory to T0. We read the registers, we read the value of the address that is in the base register T1. For the sign extension, the immediate value 4, which is the offset, is encoded on 6-bit, and it is extended to 32 using the sign extension unit. And then we compute the calculation in the ALU, where we have, for example, an address that is like 1000, and we add our 4, and we get our new address, which is 1004. For the memory access, since memread is set to 1, we have a reading operation, and so we read from memory in the new address. So what happens is, this is the memory, and what we do is just, since it is set to read, we just go to whatever address we want, we return that value in the address, and this is what's going to be written back, or in this stage. So this stage, or the write back, since we are writing back in a register, then that particular value we get from memory is going to the write back stage and going to the register file. So this is an example of a distribution of types of instructions, and this is what we've seen during quiz 2. where you have a program where with the mix of R-type 50%, load 20%, store 15%, conditional branches 10%, and finally unconditional branches or jumps for 5%. And we'll try to analyze the various components that are going to be used by this particular program during the execution, given this particular instruction mix. And so the first thing is that, for example, let's talk about the data memory. And so what kind of instructions reference the data memory? So the only instructions that are able to load or write in memory is the write or is you have your load and you have your store, right? And so in the distribution earlier, the load is 25% and the store is 10%. And so the total or the percentage of instructions that are going to use the data memory in this particular program is 35%. Instruction memory is where the code is, and so therefore it is used by all instructions. So any instruction that you have to execute, it's not going to come from anywhere else. It has to be in the instruction memory. It has to be in your code. And so given this logic, the total of the number of the percentage of the instructions that are going to use the instruction memory is 100%. So for the sign extension, it depends. Sometimes it gets ignored given certain conditions. For example, if you are using R-type instructions, the sign extension component is ignored, and so in this, as we saw earlier in the table, only load, store, and branch uses. They use all of them use the sign extension. And so given the particular distribution in the program, the load is 20%, the store is 15%, and the branch is 10%, and the total is 45%. Now for the ALU usage, we know that the R-type instructions use the ALU. We know the load and store instructions also use the ALU in order to compute the offset. And the conditional branching use it to evaluate their condition. And so in this case, given this particular distribution, R-type is 50%, load and store is 35%, we computed it earlier, and branch instructions, conditional branches are 95%. For the control flow, only branching instructions use the control flow, and so 10% given from the conditional branch and 5% given from the unconditional branch. So for the write back stage, and this should not be pipeline, should be write back stage. All the instructions that have a destination register, let's say the instruction is this, that has this format, that has some register here and something here, whatever it is, and this is the destination. This is what we care about. So all instructions that have a destination register uses the write back the write back stage, or the write back step, where you actually commit the data or commit the output to the register file. And so rtype instructions and load instructions, because you are loading from memory and putting it in a register, or rtype instructions, you are doing some math and putting it on a register. So the total is 70%. So sometimes forwarding is needed when you have one instruction is dependent on the other for its value, and the former instruction, let's say for example you have your program, right? So this is your code, and here you have line 1 until n, and let's say here we have line I and J. So let's say G depends on I, right? And the problem here is, if we do a sequential execution, we need the I to reach the write back stage in order to execute J. And so forwarding can be a solution to that, where after every stage of the pipeline, I would add registers where I can just for any subsequent instruction, they would just read from here the output in the precedent cycle and execute accordingly. And so you kind of proceed the write back stage, and it does allow us to enhance the throughput of the execution, and also it does allow to alleviate some types of dependencies, not independencies. So some key metrics that are usually used in the pipeline, and this is in this case we put a contrast between pipelined and non-pipelined execution. So if I have a non-pipelined execution, this means that my execution is like this until I reach the write back, and then I'm good. And so this is your whole instruction. This is a single instruction. Therefore, the latency for a single instruction to be executed is the sum. For the pipeline, however, since everything happens in parallel, you would have something like this. And so, in order to compute the latency, it is the max. And so for this, it's the max. So the instruction latency for non-pipeline is the time to pass through all the stages sequentially. And this is the sum as well. For the pipelined version, it is the clock cycle time times the number of stages. And this is again because of the parallel property of pipelining. So utilization, what it does, it breaks down the instruction mix to determine the component usage. And so this is some kind of low-level profiling that you can do in order to determine which stage is actually being used a lot. And some of them, if that same particular stage is slow, then it does constitute a bottleneck. And so depending on your program, different stages would be bottleneck. For example, if you create a program that has only 100% of R-type instructions, then it doesn't make sense to blame memory on the latency. And so because you have 100% utilization of the ALU and the decode stage, and so those are more important for this particular program. Now for optimization, what you do is you focus on splitting the bottleneck stage. For example, let's say memory stage is a bottleneck. So what you do is you split it, and then with that it does enhance the throughput. So let's check the example that we gave you in quiz 2. And we have every stage is using this particular latencies. These are in picosecond. And we have the same distribution as earlier. And so we're going to see how non-pipelined and pipelined are going to be executed. So for non-pipelined, like we said, it is sum of all stages, since we are doing we are executing that sequentially. And so this is what we've done here. For the pipelined, we're taking the max, since everything happens in parallel, and therefore the longest the clock cycle time is the maximum of all the latencies throughout the stages. And so in this case, memory is the slowest, and therefore it is 1500s. So for the instruction latency, like we said, for the non-pipelined, this is still the sum. For pipelined, because of the parallel property, it is the maximum or clock cycle time that we computed earlier times the number of stages, which is 5 in this case. Utilization, for the utilization, we're trying to seek what kind of component the software is trying, the program is using vehemently. And so in this case, for example, the data memory composition is, the data memory component is used by the load and write, and these are, if I remember, both of them are 35%, which is right here. And for the write registers, it is the R-type and load instructions that uses the write back stage. And so here it is 70%. And finally, for optimization, we identified that 1500 is the longest longest latency, and so splitting it would be would enhance the throughput, and that what happens here is we reduce the latency to 1000, which is the latency is either the write back or the fetch stages. Now we try to evaluate the impacts of hazards. So an example would be, so we compare, first we try to calculate the throughput, and the throughput is 1 over clock cycle time. In this case, so in this case, it is 666.7 million operations per second. And the efficiency of the pipeline, we compare it for a number of instructions. In this case, in this example, 5 instructions. And so for the non-pipeline, it's straightforward since you are executing everything sequentially. It is the multiplication. For the non-pipeline, for the pipeline, you do multiply. You do the following in order to compute. The efficiency of the stage. To compare both, you do a division, and so it means this shows that the pipeline version is 43% better than the non-pipeline version. So if there's any hazards, usually if there's a branch misprediction, then if 10% of the branches are mispredicted, in this case we have, I believe, 20% of the branches, so 10%, that's half of our branches are mispredicted, then we incur the following penalty, and this penalty is very severe because each time there is a misprediction, we have to flush the pipeline and restore the correct instruction sets that needs to be loaded. So there are three types of hazards. Obviously, when you are running things in parallel, problems may occur, and data hazards are one of them, where you have dependencies throughout your code, which is totally normal to have. But in the execution, you do have, it does imply a wait on the subsequent instructions, waiting on the precedent instructions to be written back, and so that creates a hazard. The control hazard is when it comes to branch. It usually involved what are the subsequent instructions that we need to fetch, and so in this case, some solutions would be either to add a NOP instruction or to have a branch predictor, and if the prediction is wrong, or if we have no idea what to load, then stalling is a solution also. Structural hazards happen when you are dispatching multiple instructions, and so those instructions have contention on particular components of the data path. So for example, let's say you have a multiply and an add, and both of these instructions try to use the ALU, but one of them is taken longer, and therefore the other one has to wait, and so that could constitute a structural hazard. Another one is usually when you have instructions that are especially instruction that takes a longer time to compute, for especially division and multiplication, and what happened is that these particular instruction would have the exclusive rights to the execution stage for far too long, and so waiting on those or performing any kind of instruction reordering where you take into account not only the dependency sequences but also the latency of every instruction in order to enhance the execution of your program. So, talking about data dependency, we do have three types of dependencies. Read after write, where you are reading in the second instruction and you have a write you just written in the precedent instructions. So in order to detect this particular hazard or this particular dependency, what you have is you scan the code this way, and so in this case here I have R0, I have R1 here, and I have it here, and so I have a dependency. And so you have to keep in mind that you go through the code this way, and here you have a write and here you have a read. For the write after read, it is the opposite, where you go bottom up from left to right. So you go from left to right this way, and so you have your read here and you have your write here, and you go bottom up. For the write after write, is when two consecutive or two instructions they write in the same register, and so this is the easiest way to detect it, where you only pay attention to the destination column, you don't pay attention to this, and you just look for similar registers, and so you just go up and down and detect all, list all the dependencies that you can see, or all the similarities in this case. So we do have an example, and in this case it's a simple problem of you load a value from R2 to R1, you do your addition and subtraction, you branch, and depending on the branch you would execute a multiply. So we don't know where we are branching, but this multiply is reliant on whether this branch is taken or not taken. So let's get into it. And so detecting the data dependencies, well, we don't have any for the raw dependencies. We have one instruction is dependent on R1. I mean, the add instruction depends on R1, and there's also a dependency on R3 between the add and the subtraction. Since we are having a conditional branch, there is a chance where the pipeline does not know the outcome unless this particular branch is past the execution stage, and so that creates a potential hazard for a potential control hazard for this program. And so Finally, we have the structural hazard, where there could be contention between the multiplication and the addition that can conflict in the ALU. So there is a row hazard between the load and stall, and so the solution would be either you do forwarding or stalling. And so the way you would do forwarding is you would forward the result that has been presented in the mem after the mem stage to the execution stage, where the add is going to need it, or you just insert a no operation as a stall, and that would solve it. The second hazard between the add and sub in R3, this particular one you can do forwarding as well, and what you have is add during the execution stage can forward to sub in the execution stage in the next cycle, and so that would fix the problem. For the control hazard, you can either delay the branching by a stall, or you can do some branch predictions, and that would fix the control hazard that you might have here. So for the structural hazards, reordering the add and the multiply would help into fixing the structural hazard. This is an example of the pipeline, and so this is an example of a table where it is upside down, where you have the stages this way and the cycles this way. Sometimes we put the stages, and here we put the instructions, and so I will show you that example at the end. So we start with the load. Our load has a enters the fetch stage. Then this is in the first cycle. So the second cycle, the add instruction enters the fetch stage, and we forward, and the load instructions enter the decode stage, and this is where we decode the registers and everything. And then we here we have a dependency between these two, and then we introduce the subtraction instruction, and then there is also a row between these two, and finally we introduce the branching, and it enters a control hazard because we don't know if we will load the multiply or not. And so and this is a structural hazard because there is a contention between these two. And so those are all the hazards that are in this program. And so in order to find the solutions for these hazards, is exactly what we said earlier. Either you do stalls, forwarding to alleviate the dependency, the true dependency, or you do branch prediction or reordering.